Hey everyone, welcome back to the DGA YouTube channel. In this video, I'm going to be talking about how to build decentralized games. Obviously, I can't go into extreme detail, but what I can do is provide a nice overview, something to get you started and to get you thinking along the right lines. This video is part of a series of videos about explaining decentralized games. In the first two videos, I tried to give a definition of a decentralized game and then talk a little bit about the characteristics of a decentralized game. That's the what. The third and fourth videos were trying to explain the why. So we want to look at the problems of traditional online games and then see if we can solve those. There's more information in those videos about what it is that we're trying to tackle. And of course, most importantly is what is the real benefit to the players? So if you're going to build something really complex, there really has to be a real tangible benefit to the players. And I think there is, and that's explained better in video number 4. In this video, we are going to assume that you've probably watched those and hopefully you have, or you already have a good idea. And in this one, we're going to just talk a little bit about the sort of architecture, but at a pretty high level. In making this video, I tried to come up with the main approaches, and I've tried to categorize them in a way that I think makes sense, I think that's logical, and hopefully you agree. You know, if you didn't agree, then of course you could always make a comment in the description, in the comments below of YouTube, or you can come to our Discord and chat. So I see two main ways. You can either do things on-chain or off-chain. On-chain means all of your game logic is on the chain, shall we say. It sits inside the node of the blockchain software. Or you're doing off-chain where there's a blockchain in your tech somewhere, but the actual computation is done off the chain, away from the chain. I'm not assuming that anything is centralized here. Some people think that off-chain means centralized. And while there are some games that are mostly centralized but use a blockchain for trading NFTs or whatever, I'm not assuming that here. And you will see why whenever I go through the video. You'll understand how it can actually work. Something that I want you to keep in mind, I guess these are features. Originally I think I called them principles, but I couldn't find a good word. So these are the things that are really important for decentralized gaming, I suppose any decentralized application. You have replicated state machines, which means that every computation is done by every node. It's redundant, it's replicated. These nodes or the calculations should be deterministic, so every single node, given the same input, will come to exactly the same output. And then lastly, the reason that you're doing all of this is to have consensus over player actions. That's the main important thing that actually just makes decentralized gaming work and solve the problems that it's supposed to be solving. Now let's take you through an example. So in Ethereum language, you'd have smart contracts, and if you're looking at something like Substrate or some other framework, maybe in Tendermint 2, you have modules, precompiled logic which sits inside the nodes, the blockchain nodes. All of the game logic would essentially be inside the smart contract, or the majority of it. Maybe you can mix and match and have some sort of hybrid. Doesn't really matter. Let's keep it simple here. Let's assume that all of the game logic is inside your smart contract. Obviously, every single full node has a copy of the smart contract, so there's replication, and they're all going to perform the exact same computation. Now, let's just say for simplicity that your input is 3. It doesn't matter, I just picked a number. It's like you're starting combat, and so you send in a 3, and then the chain inside the smart contract will compute something like 3 plus 4. Again, this is just an example. It's going to be more complicated than that, but let's just say it's 3 plus 4. And then, of course, the output will be 7. And every single node will have a copy of this result, which is 7. And then the response, as I've called it, it's going to be some sort of RPC pulling of data from the chain. That's going to be done by the player, and the player will see, oh, okay, it's 7. That's the result. And I think it's easy to see in that way that you can have a decentralized game because taking, say, the Ethereum network, it is decentralized and all of the computation performed on-chain is going to be decentralized. And if all of the game logic is there, then obviously the game has to be fully decentralized by default. So that's probably the simplest one to understand and the most obvious. There's good reasons not to do everything on-chain, and it's mainly around scaling, even though there are some very hard benefits that you get from being fully decentralized at layer 1. Let's have a little bit of a look at the off-chain methods, which there are more of them, and they're a bit more varied. So this one here I'm calling RNG based. I'm not sure if that's the best phrase, but let's just say it's RNG based. What happens here is you have a transaction. It's basically like a request. So there's some metadata that says, I would like to start combat. Obviously, you would make it more concise than that. It goes into the chain. The transaction is in, and then the transaction is added to the block, provided that the transaction is valid. Say there's a fee paid if that's appropriate, or the correct nonce, or whatever else. Whenever it's added to the block, there's obviously going to be a block hash of that block. And the response here could be, for example, the block hash. That's your random number. I'm not saying this is the greatest random number. There's obviously many problems with taking the block hash as a random number, but let's just pretend that it's fine for now. It's a random number. That comes back to the player, and then they derive, so this is step 4 now, the player will derive the outcome from that random number. Or of course, it's the software, it's the game software. And the game software will look at the hash, the block hash, and say, okay, this player has won the battle, or they have lost the battle. It's obviously very simple, but there's a lot more complexity that can be built into such a game. At least it may not be obvious, but it is possible. I don't really want to say too much more because obviously it's going to take a long time to go into the details. But that's a pretty obvious approach. It's pretty simple, and I think it's the sort of thing that you can use to get going quite quickly. And of course, this should be obvious, but the main computation is done by the player off-chain. The blockchain has almost no computation at all. The actual combat is done by the player. That's the deriving of the combat result or crafting result or whatever. And that's obviously off-chain. Next up is the colored coin approach, which has some similarity to rollups. I'm not going to get into the details of, what are the differences. The colored coin approach is used mainly by the Zaya team. They've been pioneering this, obviously, in the decentralized gaming space. They also have a nice blog that compares colored coins with rollups. So you can go and read that. The main idea is you have a transaction, and inside that transaction is some metadata. And here's an example that I have here. So the metadata is kind of read like this. G is a game, so game ABC, and then P is player, so it's player John inside the game ABC, performs some action, 1, 2, 3, 4. I don't know, maybe he's moving some unit from point A to point B. That's the general idea. So it's a game move, it's an action. This transaction with that metadata is sent to the chain, and then the transaction is stored on the chain, shall we say, providing that there was a fee. At least in the Zaya world, they charge fees. Not every chain will necessarily charge fees. That's another story. So at this point, the blockchain network itself has not done any computation in terms of determining whether that transaction is valid other than saying, was the fee paid? And then the response is, okay, this transaction is valid on the basis that the fee has been that the fee has been paid. The computation of combat, etc., is done off-chain by the players. And here I've got 2 players, but it could be 10 or 100 or 1,000 or whatever. Each player has the same code, and each code will perform deterministically. It's all replicated, and so given the same input, they should get to the same output. Now, their input is all of the transaction data from the blockchain. And what they do is they all compute using some rules of physics, the physics of the game, to determine the results. And that's where you will say something like, okay, if a player has a speed of 10, then they can't move at a speed of 15 because that's against the rules for that player. And all of those calculations are actually done by the players themselves in something like a game node, if you want to call it a game node. In Zaya language, they call it a game state processor. But the main idea is the bulk of the computation is done off-chain. It's done by the players who are actually interested in the results of the game, and it's not done by the people who run the nodes. People running the nodes could actually be players themselves, of course, but there's not any assumption here that it has to be like that. I'm going to move on because there's a lot more that could be said about this. It's an interesting approach, and I think it's one which will scale pretty well. In addition to that, I'm going to talk through the state channel approach. This is basically comes from conversation with the Zaya team, so it's going to be kind of slanted more towards how they do things. I'm not saying this is like the only way or the perfect way or whatever else. It's a way, and I think it's quite simple to understand. Players will create a transaction or join a transaction. Let's say it's 2, could be I think up to 10, maybe even up to 30, but with the state channel approach, it's more difficult to have like 100 players or 1,000 players. So a transaction is created, it's sent to the chain, and it's stored on the chain that a channel has been created. Players then play in a peer-to-peer manner. So that's completely off-chain. And if you remember back to the previous slide where I'm saying that the players in the Zaya network all have the same code and they're all doing the same thing, so they all have the same inputs and therefore the same outputs. At the end of a game, the winner will send another transaction to close the channel and basically declare themselves as the winner. Now, of course, there is room for attempted cheating, shall we say, and that's where there needs to be some sort of dispute resolution, because in this case of state channels, all of the actions of the players are not stored on the chain. They're all off-chain, and only basically the opening and the closing of the channel is logged on chain. So in order to do this in a fair way, obviously there needs to be some sort of dispute resolution such that one player can dispute whether the other person tried to cheat them, basically. I can't really go into a lot of detail here because I don't think I could do it justice to go into detail here that really needs to be done. And that's where you would either need to ask the Zaya team, read one of the relevant blogs, or actually check out one of our videos from the Zaya team that we have here on the DGA YouTube channel. Lastly, here, I'm calling it a virtual machine approach. Now, some of the previous approaches, like with Zaya, it is kind of like a virtual machine that they have. What it is their Zaya virtual machine, if you want to call it that, is pretty simple, and it's really tailored just to the games that they've built. What Cartesi have, for example, is that they have something which is similar to full emulation of an actual operating system. So if you look at point number 1, underneath I say that Cartesi have a RISC-V Linux. So basically it can perform all of the operations of a RISC-V Linux machine can. This is chosen, if I recall correctly, because the RISC-V is a standard. So it's something that everyone can basically be sure that there's like a standard way of doing things. I believe it is deterministic, at least the Cartesi flavor is deterministic, which is obviously one of the key properties that I mentioned before. And of course, if there's multiple machines that are deterministic and they all run the same calculation, then obviously they should get to the same output. So in this case, the off-chain virtual machine will perform the calculations of the game. It could be that you have multiple players logging into the one machine, for example. Let me just roll with that example as an idea. They play the game, and then at the end of the game, a log of the game of the actions is basically sent to the chain inside a transaction. That's added to a block, and then for some period of time after that transaction appears in the chain, there's some dispute resolution period to basically for people to complain and to dispute whether the actions were done correctly, or one person's tried to cheat another, or whatever. There's a lot more details here than I could probably really go into, and I think that's going to be one where you would have to look at the Cartesi blogs or have a look at their YouTube channel and see if you can get some details out of it. I think this approach is distinct enough from the previous approaches that it warranted basically its own slide. If you recall, some years ago there was a project called TrueBit. If you remember that, and if you know how that works, it's actually pretty similar to what Cartesi are doing. I don't know the exact differences, but if you know it, then you at least have some idea of what's happening here. And again, it's another way of taking the computation off chain to make the chain more scalable by making the chain focus only on simple things, shall we say. Okay, so that was a pretty quick introduction to the architecture, shall we say, of decentralized games, and we'll give you an idea about how you can get started on how to build a decentralized game. What I want to finish with is just mentioning the places that we have online. So we have a Discord. I need to link that to you underneath in the description. We have a Twitter. It'd be great if you could follow us. We have a website. The website isn't great, I know that. It was done in a bit of a rush. We have YouTube, obviously you're here. And then lastly, there is a book that I've been working on, which is open source. It's on GitHub, and I'm trying to basically distill all of the information from all of the people that we have in Discord and put it into some sort of coherent place, obviously as a point of reference. So, not sure I have much more to add to this video. Obviously, thanks for watching, and if you could like the video and subscribe, that would help with the YouTube algorithm and hopefully get our message out to a few more people who would or perhaps even should know about decentralized gaming. Thank you very much.